talk. And I was just not sure how tired I would be once I got here. I want to thank you very much for having me in Korea. It's been a really wonderful time so far. And okay, so I'm going to tell you about divisors on the moduli space of curves, actually on the moduli stack MGN, but I'll really focus more on some of them on M0N. And this is about joint work with Valerie Alexeyev and David Swinarski. Actually, early on in the project, Valerie's son Boris Alexeyev, did some work that we used. So it's also with Boris Alexeyev. Okay, so M0N is the moduli space of stable end-pointed curves of genus 0. And we're interested in understanding the birational geometry of the moduli space. So we want to understand all the morphisms from M0N to any other projective variety. And ideally, we'd like to know any kind of a modular interpretation for the image variety if possible, if it exists. Okay, so such morphisms are given by base point free divisors. And the theory of conformal blocks gives us a lot of base point free divisors on M0N. So I'm going to tell you about those today. So recently, work of Fakhrudin has given us the classes for a lot of these divisors, pretty much all of them. And he's given us formulas for intersecting these divisors, these base point free divisors with curves on the space. And so really we can really study these divisors. Where are they in the cone of, in the Nuff cone, in the effective cone? We can, moreover, these divisors are defined geometrically. And because of that, there's a hope that it would be actually possible to understand the images. Okay, so I'm going to introduce these divisors to you today. And I'm going to focus on a very simple family of them and what we've learned about this family. So, for example, every member of the family that I'll focus on is invariant under the action of Sn on the moduli space. So Sn moves the March points around. And so because these divisors are Sn invariant, we can think about them as divisors on the quotient M0N mod Sn. And therefore, things are easier. So let me just list. I'm going to delve right into a complicated, long example. Not complicated, but long. And before I do that, I want to just tell you what I'll tell you about these divisors. So I'm going to show you that there's a very simple formula for the intersection of the divisors with curves, which means that they're very easy to work with combinatorially. Okay, so for example, the family forms a basis for the Picard group. These are all base point free. 4 of the divisors span extremal rays of the cone, the Nuff cone. And we can identify the morphisms that the divisors define. Okay, so we do that because we have simple formulas for their classes. I'm going to show you all of this stuff, and I'm going to explain the general philosophy underlying it, how this family will illustrate how we can use these divisors on M0N to identify Nuff divisors on MGN for positive genus G. Well, actually on MG. Okay. Okay, so the goal of our project really is to do some sort of an excavation of the Nuff and effective cones of M0N. And it's based on, the hope is that we could be as successful as the program is for MG. So I'm going to tell you a little bit about what is known for the Nuff cone inside of the effective cone of MG. And it turns out that the dimensions work out really nicely. I can draw lots of pictures for M3 bar. And so that's what I'm going to do. So before I get to describing these things, let's just talk about notation. Okay, so I'm telling you about divisors on MG bar. A lot of you know all of this stuff. But just so we're all clear, lambda is the first class of the Hodge bundle on MG bar. I'm going to write delta 0 for the class of the boundary delta 0. So here's a picture of delta 0. It's the closure in MG bar of the locus of curves with the generic element has a single non-separating node. And then we have boundary classes for boundary components delta I. Boundary components delta I, so these go from 1 to G over 2. And they look like a curve of genus I and a curve of genus G minus I attached to the separating node. We take the closure of that locus in MG bar. And these classes span the Picard group. Okay, so now the effective cone of MG bar is just nobody knows. But we do know what's going on for M3 bar. So we know that the effective cone for M3 bar is spanned by delta 0 in the hyperelliptic locus, delta 0, delta 1 in the hyperelliptic locus. So let me define the hyperelliptic locus. You all know it. It's isomorphic to M0 2G plus 2 under the map that is given by taking a double cover of P1 branched along the marked points. So we know that this is an isomorphism for G equals 2. For G equals 3, the image has codimension 1 as a divisor. And for higher genus, it's smaller than a divisor. But anyway, for genus 3, the effective cone of divisors is spanned by this H3 and the boundary. So I've drawn a picture, I think, here. Now I've labeled the picture a little bit incorrectly. The back divide, so this is a cone. It really looks like a cone in 3 space. The inside cone is the Nuff cone. And the outside cone has 3 generators. Delta 0 should be in the back, and delta 1 should be in the front. And this is the hyperelliptic locus. And we're going to look at a cross-section, which has a partial decomposition into chambers. So let's look at it. Here's the picture. So what are we looking at here? In the middle, over here, there's a triangle. That's a cross-section of the Nuff cone. The bigger cone is what's called the moving cone. I'm not going to talk about that today, but this picture came from Bill Rulla's thesis, and he's identified it, so I thought I would put it in. Each of these chambers represents a variety that M3 maps to. And now, it's a birational model of M3, actually. And you can tell by where the chamber is certain things about the variety. For example, I'm going to talk about all of these chambers, but let me just point out some features. So I'm going to look at this chamber first, this top left. I'm going to go around counterclockwise. That first chamber touches both delta 0 and delta 1. What that means is that the variety associated to the chamber so it's the image of a morphism from M3 bar that contracts delta 0 and delta 1. Okay, so let's talk about these chambers. Any questions on what this picture means?
So the triangle inside?
That's the Nuff cone. The triangle inside is the Nuff cone. Something interesting about the Nuff and effective cones of MG is that for all genus, the Nuff cone doesn't ever touch the sides of the effective cone. It's always interior. So one thing that tells you is that the morphism, if you ever have a morphism from MG with connected fibers to any to any variety, it has to be birational unless you're just contracting everything to a point. And that's, a lot of the things that I'm going to tell you are true for all genus, but it's easy to draw the picture for 3. So that's what I'm doing. Okay, and I'm sure many of you are very intimately aware of this work because many of the people in this room have done this work. So let's start looking at their work. Oops, so what did I just do?
This will be easier.
I would do it myself, but everything's in Korean. Thank you. Okay. Okay, so we're going to just name all the morphisms around. I'm not going to talk in detail about them, but I'm going to use them later. And this is a good illustration, so I'm just going to name them. So the first 2 chambers have to do with different compactifications of the moduli space of principally polarized abelian varieties. So the classical Trelli map takes the moduli space of smooth curves of genus G to AG, but it doesn't extend to the Deligne-Mumford compactification. But so this map takes a curve to its Jacobian. But there are different compactifications of AG over which this morphism extends. The first is the Satake. So I'm going to denote AG bar Satake to be the Satake compactification. And there's a morphism from the from the Deligne-Mumford compactification MG bar to Satake. And this morphism is given by this divisor, lambda. So in other words, lambda is the pullback of an ample divisor from the Satake compactification of AG. Lambda is a Nuff divisor on MG. It's one of the extremal divisors. It's here, and it contracts, as I said before, this morphism to Satake contracts the boundary delta 0 and delta 1 in the Satake compactification.
compactification of AG. Okay, so let's look at the next chamber. So this next chamber has to do with the second, this toroidal compactification of AG for the second Voronoi fan. So there's another moduli space actually that comes into play that was introduced recently by Alexeyev. It's the moduli space of principally polarized semi-abelic stable pairs. And the classic Torelli map also extends to a morphism first to second Voronoi. That morphism was known by Mumford, and then Valery Alexeyev proved that it actually extended to this moduli space. That map, the second map, is a normalization over the main component of the moduli space. The main component is the component that actually contains AG. Okay, so this morphism is given by a divisor which lies on the face of the Nuff cone spanned by two extremal rays. And so let me show you the picture for G equals 3. So G equals 3 is special because these two moduli spaces are actually equal. And so this is what's going on. So if I take any divisor on the interior of this face, so here, we'll define a morphism from MG to APG. In this case, M3. Okay. So now there's another morphism. It's given by the base point free and Nuff divisor 12 lambda minus delta 0. It's been known to be Nuff for a long time, since Karl Faber's thesis, I think. And I don't know the image of the map at all. We know that there is an X, but I don't know what it is. So this is a sort of unknown chamber. Okay. Now everyone here knows the moduli space, or the moduli stack of pseudostable curves. And if we replace elliptic tails with cusps, we get a divisorial contraction mg bar to mg bar ps. And of course, this is comes out of work of was proved by Hassett, Heian, and Lee. Okay, so now this morphism is given by a divisor that lies on the face spanned by two extremal divisors, 12 lambda minus delta 0 and 10 lambda minus delta 1. So delta means the sum of all of those guys. So, you know, I think before I showed you the wrong chamber. The other chamber was here, and this is theirs, hopefully. Anyway. So this is the chamber corresponding to this contraction of elliptic tails. It's a divisorial contraction. It contracts delta 1. And okay, then there's also a small modification of that moduli space. So it contracts elliptic bridges to tack nodes. And if we compose that small modification and the contraction of tails, we get a morphism from mg bar to this moduli space of Chow stable curves. And that morphism is given by the extremal divisor 10 lambda minus delta 1 in general. So this is, look at the picture for genus 3. It's that chamber. Okay, and of course, the first flip is in the picture here too. So if we take the moduli space of Hilbert semi-stable curves, there's a morphism which is a flip of that psi. So I've drawn the picture here that you've seen lots of times, I'm sure. Now I want to just go back a little bit. So there's this morphism, let's see, I want to show you there's this morphism here and morphism here and here, but no morphism here. That's because, let me show you the picture here, the divisor that defines that flip is here. It's outside of the Nuff cone. It's in the moving cone, but outside the Nuff cone. Okay, so I'll go back to where I was. We'd like to do this for M0 n bar. And I'd like to convince you in this talk that we should, in order to do this, we should really give the conformal blocks divisors really a serious look. And so I'm going to talk about them. Okay, so each of these divisors depends on 3 parameters. So a simple Lie algebra G, a positive integer L, which is the level, and an n-tuple, one for each marked point, of dominant integral weights for G of level L. Okay, so these divisors are the first turn classes of vector bundles that are very famous. They're vector bundles of conformal blocks. So these are very
involved to define. And later today, Dave's going to actually take a shot at this, probably in detail. But I would like to say something, because I told you they're geometric, so I want to tell you what I mean by that. So Laszlo and Sorger in '95, after many other special cases by many famous people, proved that if you look over a smooth point in the moduli space, so a smooth curve, genus G, and marked points, if you restrict the vector bundle to that point, then the vector space you get, this is a vector bundle, is the global sections, it's isomorphic to the global sections of a moduli stack of parabolic G bundles on C. So it's the global sections of a line bundle on this moduli stack. The line bundle is really determined by the level, and the lambda gives you the parabolic structure. Okay, so this is a moduli space parameterizing quasi-parabolic G bundles on C determined by lambda, and the line bundle is determined by the level. Okay, the rank of these vector bundles is given by the Verlinde formula. And I'm talking about sl2 bundles here today, divisors here. So let me just show you the Verlinde formula. So this is the rank of the vector bundle. It comes up all the time in the formulas for the turn classes, for intersections with the curves. But if you just work with the properties of the vector bundle or the divisors, you can get around using such a complicated formula. That's the way to go. Excuse me? Oh, should I go? So there is no lambda. There's not supposed to be a lambda there. Oh, well, okay, so this is for SL2.
This is for lambda equals 0.
That's right, this is for lambda equals 0. Thank you. So this is even a more specific. Actually, no, Valerie. These lambdas are the i's. So, okay. Okay, so now something interesting is that for genus 0, we know these divisors are base point free. So they define morphisms. And here, Fackrudin gave an amazing recursive formula for their classes. Okay, so here's the formula. So we're taking a G as a simple Lie algebra. We have an integer, it can be 0, non-negative integer, a set of dominant integral weights of level L for G. This is the formula. So there are some technicalities in this formula. I'm showing you this formula to make an impression that it is recursive and complicated. And so these are some just minor things. These epsilons, if you're all the way up at the top in n/2, you take epsilon to be 1/2. And these r's are ranks of particular sets of weights. It's recursive. You're doing some restrictions, basically. What is it? Well, it's really complicated to say what that is. I mean, I can show. We should talk about that after. Yeah. Okay. Okay, so one thing that makes this formula great is that it holds for any conformal blocks vector bundles. And this gives us tons of divisors to work with. And unfortunately, it's recursive and hard. You saw it. And okay, so it's difficult. But Fackrudin did more. He looked at particular conformal blocks divisors, and he sort of got us started on how to think about them. So for example, just tell you some of the things he showed. So he looked at SL2 level 1 divisors with non-symmetric weights. So for level 1, that means these are just integers 0 or 1. And he showed that this family forms a basis for the Picard group of M0 and bar. And so some of them are 0. And he proved, there's a lot that goes into this. It's maybe 2 pages of proof. And
You really mean a basis or
a basis, a Q basis, not a Z basis. And also, so Valerie was visiting Tata and talked to Fackrudin. He can tell you the story better than me, but they were talking, and Fackrudin knew a lot about what curves the divisors contracted, and Valerie pointed out to him that actually those divisors give morphisms that factor through.
It's not obviously that you have the same number of divisors.
Right, so there are a lot of them are 0. So for example, if you have an odd number of ones, if your weights sum to an odd number, then you get something that's 0. So once you pick the first n minus 1 weights, the next one is defined. So that gives you 2 to the n minus 1. And then some more of them also are 0. I mean, a lot of time, in fact, these conformal blocks divisors that I'm going to tell you about really aren't even defined. They're trivial when you're dealing with n as odd. Okay?
So you're saying the non-zero divisors?
Yeah, the non-zero ones. That's right. Okay, so I'm going to focus on a completely different simple family, much simpler than Factorinans. So we're going to look at this family of divisors. We're going to take all weights 1. The thing about taking weight 0, once you have a weight that's 0, you can write as a pullback of something from a smaller m0n. So we just start with weights 1, and we're letting the level vary from 1 to g. So what is this g? So one of the things I may have glossed over, I said that, so one of the facts proved by Factorinan, which I think is on the next slide, is that if the sum of the weights lambda I is odd, then the vector bundle is 0. So the divisor is 0. So d sl2 lambda bar is trivial. Okay, so for example, if you just take weights all 1, so there are n of these, and if n is odd, well, then that's the sum, and they're trivial. So we assume, first of all, that n is even. Now, these divisors, so n is even, that's one restriction. So I'm going to write it as 2 times something. I choose to write it as 2 times g plus 1. And some of these are Sn invariant, so these are divisors on m0n mod Sn. If you write n like this, then you get a space that they're defined on that's isomorphic to the hyperelliptic locus. So that's why I'm picking g here. Okay, so I'm going to write n as 2g plus 1. And this is what this g is in this set. Okay, so this is a family defined by g equals sl2. We're taking our level to go between 1 and g, and symmetric weights lambda, all ones. Okay, so why are we looking at this family? Well, this is what I just told you here. For any level and lambda, if the sum of the lambdas is odd, then the rank is 0. So in particular, if n is odd, then this divisor is trivial. And also Factorinan showed that if the weights are less than or equal to 2 times the level, then the divisor is trivial. So in other words, if the level is too big, then the divisor is trivial. So we're stuck with looking at levels between 1 and g. Okay, they're Sn invariant, I've said that. And so we're going to look at them in the symmetric Nuff cone of m0n or the Nuff cone of this quotient. And this moduli space m0n tilde for n equals 2g plus 1 is isomorphic to the hyperelliptic locus. In particular, it has Picard number g. Okay, so this is what we're going to do. These are the features of the family. I'm going to give you a formula for intersecting these divisors with f curves, a basis of 1 cycles for the a collection of curves that gives you a basis for 1 cycles. And we can see from this that these divisors form a basis of, that should be m0n tilde. So that's a typo. It should be a basis for pic m0n tilde. And actually that 4 of the members of this family span extremal rays of the Nuff cone. Okay, so I'm going to give explicit formulas for their classes, and as an application, we're going to study the morphisms. Okay, so I'll just remind you that, or tell you for the first time, that if you're dealing with the symmetric Picard group, or the Picard group of m0n mod Sn, then a basis is given by sums of divisors. I call them bk. Some people call them bk tilde, where you take the sum of all divisors delta A on the moduli space, indexed by sets of size k. So I didn't tell you what those are. So here we're on the moduli space m0n bar. And the boundary divisors here are loci of curves that have at least one node. The generic element has a single separating node, and I'm indexing it with a subset of the marked points. So on the generic element, you have some marked points, and on the other side you have some marked points, and this side has marked points indexed by the subset A, and then A complement. That's just the generic element. We're taking the closure of this locus in M0n. And then the idea is that if the symmetric group is acting and moving the points around, we don't really care the names of the marked points. So, so the class of this, by the way, the class of this in the Picard group, I'll call delta A. And if we're looking at M0n mod Sn, then really we just need to sum all these boundary divisors together, these boundary classes of the same size. And those will give us generators for the Picard. Okay. So in order, I'm going to give you formulas for these divisors in terms of that basis. And so to do that, we need to know how to intersect the divisors with curves. And so we're going to use a collection of curves that are called F-curves. They're one-dimensional. They're any curve that's numerically equivalent to a one-dimensional boundary strata. Okay, so an F-curve is any curve numerically equivalent to a one-dimensional boundary component. So this curve only depends on really just a partition of the marked points into 4 sets. And then if you're working mod Sn, it only depends on the size of those sets. So the idea is really all those one-dimensional boundary components are images of morphisms from M04. And what are the morphisms? Well, you take so this is all one-dimensional boundary of M0n are isomorphic to M04. So I'm going to define a morphism. Lots of morphisms are defined this way. All I have to do is specify a partition of my marked points into 4 sets. And I attach a pointed curve with those marked points. When I draw this picture, I'm really just attaching a point. So this means a point in M0 size of A plus 1. And I'm attaching this plus 1 here. And I would do that with, similarly, just a point in M0 size of B plus 1, etc. So the image really is just one-dimensional, because I'm just attaching points. And then any curve that's numerically equivalent to such an image gives me one of these boundary curves. And if I work mod Sn, so on this, an F curve is just given by a partition of the set, is determined by the size of that partition, A plus B plus C plus D equals N. Okay. Okay, so, and I've said this, a partition of the integer into n, integer n into 4 positive integers determines an F curve up to symmetry. And we're going to denote that curve FABCD. So it turns out that this set of F curves where you just have 1, 1, I, and n minus 2 minus I, so there's a 1 and 1 here. The set of all of these, as I goes between 1 and, in this case, n over 2 minus 1, this set is actually a basis for the 1 cycles. And we have an explicit way of writing any F curve in terms of this basis, and I think that Dave will present that formula in his talk. So we just need to know how to intersect our divisors with these curves. So I'm going to tell you the formula, and I need just a little bit of notation for that. So I'm going to just use this notation, RLJT. That's going to be the rank of the conformal block vector bundle determined by SL2, L, and then this j plus 1 tuple where you have all ones in the first j slots and then a t. And here's the theorem. If you take an intersection of the level L sl2 divisor with one of these curves, it's a product of these two ranks. Okay, so here are two immediate corollaries of that. First of all, we know, because we have formulas for when these ranks are 0, lots of formulas from Ferran and also things that we've done, it turns out that you can show that the divisor will intersect this curve, will kill this curve, if and only if I is not congruent to L mod 2. I'm going to do an example in a sec. You look unhappy.
The product representing the 4 indices? What is it?
There were 4.
Now there are only 3.
Yeah, there's 1, 1, I, n minus I minus 2.
The next 4.
Oh, about this? Oh, well, yes, that's sloppy notation. I mean, once you know how to write n as, I mean, you know that you're giving a partition. So if I write 1, 1, I know that whatever's here has to have the property that 1 plus 1 plus I plus question mark has to add up to n. So in other words, that's f of 1, 1, I, n minus I minus 2. And I just stupidly left out of the file. Sometimes, you know, so that should have an n minus I minus 2. Okay. Okay, and then as a corollary also of that intersection formula, you can show that these divisors form a family of, this family of divisors forms a basis. So let me show you kind of what the proof, how the proof goes by showing you an example. Yes, that should be yes, that should be a tilde. That's a typo. So these guys are a basis. Let me erase and have space. I'm going to show you I'm going to let you gaze at the example while I write that up, okay? So here's this example. So this is example for n equals 16. So this set, let me fix the typo, sl2, all ones, well, L is going between 1 and G. And here n is 2 times G plus 2. And this forms a basis for pick M0 n mod Sn, or M0 n tilde. Okay, so here we have n equals 16. So 16 is equal to 2 times 8. So if we write it like this, it's 2 times 7 plus 1. So the genus is 7. So there are 7 of these divisors. They're pictured on the top. So I wrote 1 bar instead of 1, 1, 1, 1, 1. And then on the left, in the column on the left, is the basis of 1 cycles, these curves. And these numbers represent the intersections of the divisors with the curves. So you can see that this has full rank. So, and also, you can see in the first and the last column, the first 2 columns and the last 2 columns, a lot of curves are getting killed. It turns out that these are the divisors that are extremal in the Nuff cone. Okay, so these divisors, DL1111, where L is 1, 2, G minus 1, and G, generate extremal rays of the symmetric Nuff cone. Okay, so I'm going to show you why. So we see this because we see what curves they intersect in degree 0. Okay, so this vector space is G-dimensional. So if we have any family of G minus 1 linearly independent 1 cycles, curves, effective curves, that the divisor kills, that'll mean that that divisor, if it's Nuff, is extremal in the Nuff cone. Okay, so we're going to use these F curves. So let's look at the first one. So that theorem said that with level 1, we're going to get an intersection if and only if the product of the numbers that define the curves is congruent to 0 mod 2. Okay, well there are lots of curves like that. It turns out that if you take the set of curves 2, 2i, n minus I minus 4, there are g minus 1 of these curves. These happen to be independent, and so these curves tell you that this is an extremal divisor. So this divisor is extremal. Let me show you a picture of what it looks like. So let's look at n equals 8. This is the Nuff cone for M08 tilde. So this is spanned by B2. I wrote it up here because I didn't label the extremal rays. B2, B3, and B4. This is a cross section of the Nuff cone. Each of those lines represents one of these F curves, and it turns out that these F curves actually generate the Nuff cone for this moduli space. That's a conjecture that they always do, but it's not known for all n. So the chamber in red is the Nuff cone. Now let's look at which of these curves intersect this divisor in degree 0. So lots of them. So this divisor is here. We don't need all of them to prove it's extremal. We just need 2. And anyway, that shows it's extremal. And it's this extremal ray of the Nuff cone. So the second one is similar. We know that by that theorem that the intersection of the divisor with this F curve is 0 if and only if the product is congruent to 1 mod 2. And so we have a set of these curves. We take 1, 1i with I odd and 3, 3i with I odd. There are g minus 1. You don't have to take all of these. You can take a subcollection of g minus 1 of them. And so let's consider the example for n equals 8. Here's our picture of a cross-section of the Nuff cone inside of the effective cone, M08 tilde. These are the curves that intersect D2, 0. And we only have 2. And in fact, they turn out to be independent and show that it generates this extremal ray of the cone. Okay, so g minus 1, same thing. Remember in that example I showed you, g minus 1 was the second to last column, and it was all zeros except for 1. That's the family we take. So that's the family of curves. We take just a subcollection, all but one of the basis curves. And for the last divisor, we take all but the last basis curve. And these curves are independent, so dg is extremal. So we can see the picture for n equals 8. So that's one of them. Now, for n equals 8, so this is kind of a constrained picture. 8 is 2 times 4, so the genus is 3. So in fact, dg minus 1, in this case with g equals 3, is actually d2. We've already talked about that one. So the last one here is D3, and that's the one I'm picturing here. Now, the Nuff cone of M08 tilde has 4 extremal rays, and this is the simplest family you can write down. It generates 3 of them. The 4th one is given by another kind of conformal blocks divisor that Dave's going to talk about later today, SL in level 1. Okay, so I want to just tell you what the morphisms are for these extremal rays and some of the faces that they span. And so let me just do that. So the first one actually defines a composition from M0 2g plus 2 along this isomorphism of the hyperelliptic locus. So it goes to hg, sitting inside of mg, and then with the Satake map all the way to AG Satake. So how do you show that? Well, first of all, let's look at a picture. So remember the Satake chamber in the Nuff cone of M3, this first example I showed you. So that was given by this divisor lambda, and this is the effective cone for M3 bar. If we pull that back to M08 tilde, this is what we get. This is our conformal blocks divisor. I'm not suggesting this is a chamber of M08 tilde. I'm just telling you what divisors pull back. The chamber actual decomposition of M08 tilde probably looks something more like this. but this is just a pulled back M3 chamber. Okay, so what I'm saying is that when you pull back lambda to the Nuff cone of M08 tilde, you land on this conformal blocks divisor. Okay, this is the picture for M3, but how do you know it in general? Well, we computed the class of the divisor. This is the class. Now I want you to remember Factorin's class. This is our class. It's a little simpler, I think. And these are simple divisors, really simple. And so the BK in the formula are the sums of delta I where I has size k. That should say I has size k. Anyway, one can show that if you just, the pullback formulas for this map for pulling back lambda are well known. And if you pull back lambda, you get this divisor. When I write equality there, I mean proportionality. It's a multiple of. Okay. Now the second divisor, the second extremal divisor, actually defines a map to that unknown variety x. So let me remind you of the picture. So we had that one chamber in that nice picture that we didn't know the image variety, no modular interpretation. And if we pull it back, we've got a line, and we don't know the image variety. So that's an open question. What is it? We know that there's a morphism, though. And we know some properties of the image variety because of where it sits in the cone. Okay, so now how do we prove this? Well, we wrote down the class, and we just checked that the pullback of 12 lambda minus delta 0 is actually proportional to this class. Okay, so now kappa 1. So kappa 1 is an ample divisor on M0 2G plus 2. And we can see with this that it actually defines a map all the way to this moduli space of semi-abelic pairs. So how do we do that? We showed that kappa 1 is proportional to a combination of the two divisors. So let me show you in the picture for G equals 3. So this is the second Voronoi chamber here. And when we pull this back, we land inside of the Nuff cone of M08 tilde. Okay, so now the last two extremal classes look like this and this. So they're fairly nice formulas. In general, you can't see that these formulas are pulled back along, pullbacks of divisors, Nuff divisors along the hyperelliptic map. For low G, it works. Like, for example, for G equals 3, it does. And I'll show you that. But in general, no. But we can identify their morphisms anyway. So, so let's just look. Okay, so they're not pulled back along the hyperelliptic locus in general, but they are for G equals 3. So after I show you the picture for G equals 3, we'll talk about where these, what's going on with these divisors. What morphisms do they define? Okay, so G equals 3. I told you earlier that G minus 1 is D2. And so the last one is the last extremal divisor is this D3 divisor. Level 3, sl2, weights 1. Okay, so remember the Chow stable chamber of the cone. So that was this is the chamber, this corresponds to the variety which you get by first contracting elliptic tails and then elliptic bridges. And you can show that actually that divisor that defines, so the divisor on, this is a divisor on the Nuff cone of M3 bar, it defines the morphism from M3 first by contracting tails and then elliptic bridges to this variety. It actually pulls back to this Nuff divisor D3 on M08 tilde. And that means that there's a morphism. Did I write it? So let me write the morphism. So that means that we have this morphism from M08 tilde to M3 bar, and then to MGCS, M3CS. Well, in fact, yes, M3CS. So a lot of these statements have been for all genus. This is just a genus 3 statement. So this is psi after T. And this is given by D3 In other words, this divisor is the pullback of the map that defines the divisor. Well, okay. So let's just look at the big picture for M3 and M08 tilde. So this is interesting. All these chambers pull back to some chambers of M08 tilde. We don't think these are the this isn't the so-called chamber decomposition. It's not true necessarily that every divisor in the colored in areas corresponds to the same variety. But it's some, understanding that we didn't have before, some start of a chamber decomposition. Bill Rula, who started drawing these pictures in his thesis, has, I think, some way more complicated picture for M08 tilde that looks like this. And I think, so this is the Nuff cone that we've been looking at, and this is his conjectured moving cone. Or did he prove it's the moving cone? I'm not sure. But anyway, there are lots of different possible ways of doing things. One thing I think that's interesting is that there is a conjecture that there will be a chamber decomposition for M08N. That doesn't have to be true for a general variety. I mean, it doesn't have to be true. But M0N is conjectured to be what's called a Mori dream space. And if it is, then there will be a chamber decomposition. We know it is for n equals 6. That was proved by Anna-Maria Castrovet, who's here at the conference. So we can hope that there is. Okay. Now, oh, right. So I wanted to tell you that the last extremal divisor was known already to give a decomposition, to give this morphism from M0N to a GIT quotient. Some people in the audience will recognize this notation because it's theirs. So Alexei Swinarski studied this divisor before. It just was a coincidence that it came up again. And this morphism with this notation has been studied by Kim and Moon. So this morphism to this GIT quotient factors through a sequence of contractions through the Hassett weighted moduli spaces. So if you want to learn more about this decomposition, you can look at their paper. And now, okay, so morphisms can define, of course, can define morphisms that, divisors can define morphisms that factor through lots of different spaces and end up at isomorphic varieties. And so I've just showed you one interpretation for those conformal box divisors, for the morphisms they define. But they actually, all of these extremal divisors, also the morphisms they define factor through the flag map. So there's a morphism, the morphism from M0 and tilde to Mn, moduli space of curves of genus N, it comes up because it's a tool for finding Nuff divisors on moduli space of positive genus curves. So there's this map, M0N. This is a morphism to Mn. And it's given by attaching elliptic tails. So every time I do this, I bring the genus up by 1. So I end up with a genus N curve. And I'm calling this map F for flag. And it turns out that if you take all of those extremal divisors, you can see that there are pullbacks of Nuff divisors from M2G plus 2. In fact, often more than one divisor will pull back. So you can have up to 3 pulling back to 1, 3 extremal divisors. Often you'll have 3. Okay, so what I'm saying is that there are positive constants Cj and Nuff divisors Dj on M2G plus 1, so this moduli space of positive genus curves, such that for these divisors, you can show that when you pull back this Nuff divisors that you're solving for, you get something proportional to our extremal divisors. So what that says is the morphisms that are defined by these extremal divisors factor through this map. Okay, so let's look at n equals 8. So I can't draw the Nuff cone for M8. It's too big. But I'll just tell you what happens. So there are 20 extremal Nuff divisors on M8 bar. 3 of them pull back along this map to 0. 2 of them pull back to sl2 level 1. 2 pull back to sl2 level 2. 3 of them pull back to sl2 level 3. And all but 2 of the remaining 10 pull back to combinations of 2. So they lie in faces spanned by 2. And the other 2 are just, you can write them in as a sum of 3. And so this is just the simplest family, and yet when you're pulling back divisors along this flag morphism, you're hitting these divisors. And this has significance because of a theorem that says that, so here's a theorem, and this is me, Keel, and one of the organizers, Morrison. If D is an F divisor, I'll explain what that means in just a second, on N, so this is moduli space of genus N curves, and if you pull back D to M0N, and you get something Nuff, then D is Nuff. So these conformal blocks divisors, which we know are Nuff on M0 and tilde, can give us a tool for identifying Nuff divisors on the moduli space of higher genus curves. And we can see that here. Okay, so I want to summarize. The theory of conformal blocks has given us many base point free divisors. I mean, we looked at just a few, just tiny tip of the iceberg. And thanks to Ferran, we have access to their classes and for intersecting them with F-curves. And that means that we can learn about the morphisms that they define. We can learn about them by knowing what position they are in the Nuff cone. We can maybe compute their classes and see actually that they're pullbacks of something. And presumably, as these guys are defined geometrically, I think we have a good shot at maybe finding the key to understanding, we see one of these, what should the morphism be? So that's the end of my talk.
Any questions?